I'm going to be discussing what is word embeddings in NLP. So, word embedding is an approach for representing words and documents. Now, word embedding or word vector is a numeric vector input that represents a word in a lower dimensional space. Method of extracting features out of text so that we can input those features into a machine learning model to work with textual data, which allows words with similar meanings to have similar representations. The similarity can be assessed based on similar vector representations. Right now, what is the need for word embedding? To reduce the dimensionality, to use a word to predict the words around it, helps in enhancing model interpretability due to numerical representation. Interword semantics and similarity can be captured. Now, how are they used? So they are used as input to ML models. Words are given a numeric representation, which are used in training or inference in ML models to represent or visualize any underlying patterns of usage in the corpus that was used to train them. Right now, approaches. So we have different techniques in embeddings in natural language processing (NLP). Types of word embeddings. We have three types, right? So frequency-based embeddings, prediction-based word embedding, and contextualized word embeddings. First, we have the frequency ones, frequency-based. So it has basically mainly three types: bag of words, TF-IDF, and co-occurrence matrices. Then prediction-based word embeddings includes word to vector, CBOW, and skipgram. Then glow vector, glow and fast text. And contextualized word embeddings, Elmo, BERT, and GPT. So we basically will be discussing each and every one in quite depth. So stick till the end. I'll explain every single thing, right? So the conventional method involves compiling a list of distinct terms and giving each one a unique integer value or ID, and after that insert each word's distinct ID into the sentence. Now, common traditional methods I'll be discussing. First, we have the one-hot encoding, which is a simple method for representing words in NLP. In this scheme, each word in the vocabulary is represented as a unique vector. Each word is given a representation as a unique vector, where the dimensionality of the vector is equal to the size of the vocabulary. Now, the vector has all the elements set to 0, except for the element corresponding to the index of the word in the vocabulary, which is set to 1. Now, one-hot encoding, the disadvantages are it has high dimensional vectors, computationally would be expensive and memory intensive, does not capture the semantic relationships, and is restricted to the scene training vocabulary. Now, this is the Python code. You can see one-hot encode the text that is given to us, right? This is the text, and we basically, let us say, firstly we have the vocabulary. Let us see the output. This is the vocabulary given to us. Word to index mapping, I created a map, right? So that would basically give us the index of the particular word that we are at. One-hot encoded matrix would be giving us the vectors and the index where the element is present. For example, cat is present at 6 index, right? So in this vector, the size of the vector would be the same as the size of the vocabulary, as it was mentioned here. And at index 6, we have cat, so that will be marked as 1. All the others are marked as 0, right? So similarly for in, we have it at index 1, so index 5. So index 5 has been marked as 1. All the others are 0. Similarly for all the other words you can see in the vocabulary, the word to vector, sorry, one-hot encoding matrix has been shown. Then we have bag of words. So it is a text representation technique that represents a document as an unordered set of words and their respective frequencies. It discards the word order and captures the frequency of each word in the document, creating a vector representation. Limitations are, again, ignores the order of words in the document, causes loss of sequential and semantic information and context, and it has sparse representations which make it memory intensive. Many elements are 0, resulting in computational inefficiency with larger data sets. So this is the code for that. We use the count vectorizer function from sklearn.featureextraction.txt, and we basically fit transform the documents and get the feature names out and printing them out. So this is the bag of words matrix. Vocabulary, we had this, right? Then we have TF-IDF, which is term frequency inverse document frequency. It is a numerical statistic method for textual data that reflects the importance of a word in a document relative to a collection of documents, which is a corpus. And it's used in NLP and information retrieval to evaluate the significance of a term within a specific document in a larger corpus. It has two components: term frequency, which measures how often a particular term is occurring in a document. Term means a word in one particular document, how frequently it is occurring. And inverse document frequency is the importance of a term across the collection or the corpus that is present with us. So TF-IDF is basically TF of the term in the particular document, T comma D, and the IDF is IDF is basically the inverse document frequency. Now the formulas are given here. Term frequency is total number of times the term T appears in document D upon the total number of terms in that particular document. And inverse document frequency is basically the total documents that we have upon the number of documents that have the term T, and we take the log of that. That is the inverse document frequency. So the higher the TF-IDF score for a term in a document, the more important or the more weight it is given in the document within the context of the entire corpus. Now, this weighted scheme helps in identifying and extracting relevant information from a large collection of documents and is commonly used in text mining, information retrieval, and document clustering. Steps are as follows: define a set of sample documents, use TF-IDF vectorizer to transform these documents into a TF-IDF matrix, extract and print the TF-IDF values for each word in each document. This helps us assess the importance of words in a document relative to their frequency across a collection of documents, helps in information retrieval and text analysis tasks. So from sklearn.featureextraction.txt, import TF-IDF vectorizer. Documents we have given we have been given two documents. The First document contains this text. Document 1 has quick brown fox jumps over the lazy dog, and document 2 has a journey of 1,000 miles, begins with the single steps. Vectorizer is the TF-ID of vectorizer, which we declared from here. Then we declare the TF-ID of matrix using fit transform function, and feature names, we get out the feature names, and we're printing. So document 1 we get the TF-ID of score, and document 2 we get the TF-ID of score, right, using this TF-ID function, right. Now, some of the disadvantages are that inability in capturing context. It doesn't consider the semantic relationships in the words, and it is sensitive to document length. Longer documents have higher overall term frequencies, potentially biasing the TF-IDF towards the longer documents as well. Now, neural approach. So we have word to vector, which is a neural approach of generating word embeddings. It belongs to the family of neural word embeddings techniques, and specifically falls under the category of distributed representation models. And it is popular in NLP. It represents words as continuous vector spaces. AIM captures the semantic relationships between words by mapping them to high dimensional vectors. Right. Words with similar meanings should have similar vector representations. Every word is assigned a vector. We start with either a random or one hot vector. So we have two neural embedding methods for word to vector: continuous bag of words (CBOW) and skipgram. Now let us discuss the CBOW. So it is a type of neural network architecture used in word to vector model. Primary objective of CBOW is to predict a target word based on its context, which consists of the surrounding words in a given window. Given a sequence of words in a context window, the model is trained to predict the target word at the center of the window. Feed-forward neural network with a single hidden layer, the input layer, hidden layer, and output layer represent context words. Learn continuous vectors or embeddings and the target word, and it is useful for learning distributed representation of words in a continuous vector space. Right. So this is the code for that, and you can see the output. Then we have skipgram model, which learns distributed representations of words in a continuous vector space. Main objective of skipgram is to predict context words surrounding a target word given a target word. This is the opposite of CBOW, where the objective is to predict the target word based on its context. So we predict context words based on a given target word. In CBOW, we predict the target word based on the context, right? And we have the method. Output is trained vectors of each word after many iterations through the corpus. It preserves the syntactical or semantic information, converted to lower dimensions. Similar meaning, that is semantic information vectors are placed close to each other in space, and vector size parameter controls the dimensionality of the word vectors, and we can adjust other parameters such as the window size, etc. Note that the word to vector models can perform better with larger data sets. If you have a large corpus, you might achieve more meaningful word embeddings, and this is the code for that. I'll put the link in the description of this whole document, right? Now, the choice between CBOW and skipgram depends on data and the task. CBOW might be preferred when training resources are limited. We have a smaller data set, and capturing syntactic information is important. Skipgram is important when semantic relationships and representation of rare words is important. Right, so that's it.